When we talk about the observable universe, we are dealing with what we can see, measure, and record, based on the light and other radiations that reach us. The cosmos may be much larger than what our instruments can capture, but there is a physical limit called the cosmic horizon. This horizon is not a material barrier, like a wall or a fence, but rather a conceptual frontier imposed by the very speed of light and the age of the universe. Light is the fastest messenger that exists, and even so it needs time to cross space. Since the universe is approximately 13.8 billion years old, the light emitted by more distant objects simply has not had time to reach us. This creates a sphere around the Earth that defines everything we can observe, the so-called visible universe. However, there is an important detail. The expansion of space makes the observable horizon larger than 13.8 billion light-years. This happens because while light was traveling here, space itself was expanding, pushing galaxies even farther away. That is why the distance to the limit of the observable universe is approximately 46 billion light-years in any direction. Imagine a gigantic sphere with the Earth at the center, not because we occupy a special position, but because every observer at any point in the universe would have the same limited vision by their own cosmic horizon. This value, 46 billion light-years, is so incomprehensibly large that even when trying to convert it into absolute numbers, we end up resorting to scientific notation. In fluid terms, it is like saying that the visible universe extends for tens of billions of trillions of kilometers. This idea of the cosmic horizon is supported by fundamental observations, such as the cosmic microwave background radiation. This extremely faint glow detected in all directions of the sky is the echo of the Big Bang, the oldest light we can capture, coming from a time when the universe was only 380,000 years old. Before that moment, the cosmos was so dense and hot that light could not pass through the primordial plasma. It is like trying to see through an impenetrable fog. Only when the universe cooled and atoms formed could radiation travel freely, creating the background curtain that marks the limit of our vision. The cosmic horizon, therefore, is not only a matter of distance but also of time. Every time we look at very distant objects, we are looking into the past. A galaxy 10 billion light-years away is not seen as it is today, but as it was 10 billion years ago. When we reach the limit of 46 billion light-years, we are practically looking at the beginning of the universe. This combination of space and time makes the observable horizon a kind of cosmic memory capsule, revealing fragments of the history of the universe in every direction we point our telescopes. Another intriguing point is that the observable universe is not fixed. Every second, space continues to expand, pushing entire regions full of galaxies beyond our reach. This means that in the distant future, many of the galaxies we can observe today will no longer be visible. They will be so far away that the light they emit will never reach the Earth. This perspective transforms the observable universe into a temporary window, a unique opportunity to contemplate certain parts of the cosmos before they disappear forever from our horizon. With this, we understand that the observable universe is only a cutout of the total reality. There may be much more beyond our vision, but we are limited by a natural frontier that we cannot surpass. Even so, within this sphere of 46 billion light-years, we already find hundreds of billions of galaxies, each with billions of stars and possibly countless planets. It is a reminder that even without knowing what lies beyond, what we can observe is already vast enough to challenge our imagination. When we talk about what lies beyond the cosmic horizon, we enter a territory where science relies on deductions, mathematics, and physical models. Since direct observation becomes impossible, we know that the universe has a finite age and that light travels at a limited speed. This means that we can only see a fraction of the whole, a kind of bubble around us. However, there is no reason to believe that the cosmos ends exactly where our vision stops. On the contrary, the most accepted cosmological models indicate that there is much more universe than we can see, perhaps even an infinite reality that extends without limits. This idea gains strength when we consider the uniformity observed in the cosmic background radiation. It shows that the universe is incredibly homogeneous and isotropic, meaning it has practically the same properties in all directions. If the universe is so similar within what we can observe, It is reasonable to assume that it continues to be so beyond the horizon. This means that beyond the 46 billion light-years we can detect, there may be more galaxies, more stars, more planets, and perhaps even more civilizations. The difference is that their light has not yet had enough time to reach us. The accelerated expansion of the universe, discovered at the end of the 20th century, complicates this picture even further. Due to dark energy, space not only expands, but does so at an increasing rate. This creates regions of the universe that are moving away from us faster than light can travel. These places will never be seen, no matter how much time passes, because the light they emit will never reach the Earth. It is as if they are forever hidden behind an invisible veil. This phenomenon creates the concept of an unobservable universe, which may be as vast as or even larger than the universe we can see. What makes this discussion fascinating is that what lies beyond the observable may have an impact on our understanding of reality. For example, if there are variations in the distribution of matter in distant regions, they could influence the way our local universe evolves. Although we cannot see these regions, their gravity could, in theory, exert subtle effects. Research into anomalies in cosmic radiation has already raised hypotheses that we may be detecting echoes of structures far beyond our horizon. From a human perspective, what exists beyond the observable is almost a paradox. We know it is there, but we will never be able to look directly at it. It is like living inside a room illuminated by a small window. We see only a fraction of the landscape and know that there is much more world beyond, but we cannot open the wall to observe the whole. This limitation raises profound questions. Are we condemned to know only a part of the universe? Will our instruments always have an insurmountable limit? Even so, science continues to try to push the boundaries of the observable. Ever more powerful telescopes bring us closer to the horizon, capturing light that is older and farther away. Gravitational wave observatories seek to detect signals from cosmic events that may come from regions beyond what light reveals. These attempts, even if they do not directly show what lies beyond the horizon, can give us valuable clues. With each advance, the sphere of the known grows a little larger, but the unknown grows even faster. In the end, the greatest lesson of the universe beyond the horizon is humility. We live in a cosmos that seems to have no limits, but our vision is restricted to a finite bubble. What lies outside it may be similar to what we already know, or it may hide surprises we have never imagined. This uncertainty is at the same time a limitation and an inexhaustible source of scientific curiosity. One of the greatest questions of cosmology is whether the universe is finite or infinite. This question may seem simple, but it hides profound complexity, because the universe can have different geometric forms that determine its destiny and its extent. Since the equations of general relativity formulated by Albert Einstein, we know that the geometry of space is not rigid. It can curve under the influence of matter and energy. Thus, the question is not only how big is the universe, but rather, what is the shape of space itself? Cosmologists have identified three main possibilities: a closed universe, an open universe, and a flat universe. In a closed universe, space curves in a positive way, like the surface of a sphere. In this model, if you traveled in a straight line long enough, you would end up returning to your starting point, as happens when circling the Earth. This type of universe would be finite in extension, but without edges. There would be no abrupt boundary, only a curvature that leads the path back to the initial point. In the case of an open universe, the curvature is negative, like the surface of a saddle. In this model, space would expand forever, never closing in on itself. This would represent an infinite universe without limits of extension, in which expansion would never end. In the flat model, space presents no global curvature. It extends in all directions uniformly, like an infinite sheet. This is also a scenario of infinitude, but with a simpler geometry and without return to the starting point. Modern measurements, especially those made on the cosmic background radiation, indicate that the universe is incredibly close to flatness. This means that, within our margins of error, it does not appear to curve positively or negatively on large scales. This conclusion suggests that the cosmos may be infinite in extension, something difficult to imagine. When we think of infinity, we are not only talking about distance, but also about content. Infinite galaxies, infinite stars, infinite planets. perhaps even infinite versions of stories similar to ours happening in regions so distant that we will never be able to reach them. The concept of infinity in space brings profound implications for physics and for philosophy. If the universe is truly infinite and homogeneous, every possible configuration of atoms should repeat somewhere. This means that identical or almost identical versions of ourselves could exist in points so distant that light would never have enough time to travel there, even in the entire lifetime of the cosmos. This idea, although a logical consequence of infinity, challenges our sense of individuality and uniqueness. On the other hand, the notion of a finite universe without edges is also fascinating. A closed cosmos reminds us that limits can exist without tangible frontiers. It is like living on the surface of a sphere. Walking always forward, we would never encounter a wall, but we would still be inside a finite structure. This model, although currently less likely, reinforces that the geometry of the universe is one of the keys to understanding its essence. In the end, the debate between curved space and flat space shows us how mathematics is fundamental to understanding reality. Even without being able to travel to the ends of the universe, we can, with equations and observations, test hypotheses about its shape and its destiny. Infinity, whether real or only an abstraction, remains one of the greatest frontiers of the human mind. If the universe is truly infinite, we enter a realm where human imagination reaches its limits. Unlike a finite space, in which we can at least conceive of a maximum extension, infinity has no boundary, ends nowhere, and cannot be contained within simple numbers. When we apply this notion to the cosmos, the consequences are vast and, in many cases, unsettling. An infinite universe does not only mean more stars and more galaxies, it means that all possible configurations of matter and energy can exist somewhere, even if at unreachable distances. In this scenario, concepts such as cosmic duplication emerge. If space is truly infinite, and if the laws of physics are universal, then, statistically, the combinations of atoms that form you, the Earth, and everything we know should repeat. Somewhere, at an incalculable distance, there could exist a galaxy identical to the Milky Way, a planet identical to Earth, and even a version of yourself living an almost identical life. This is not a mystical statement, but a mathematical consequence of infinity, combined with the repetition of probabilities. This notion, though intriguing, creates discomfort, as it dilutes the idea of the singularity of our existence. Another point is that in an infinite universe, the limits of time also become questionable. If there are infinite worlds, each with its stars and histories, then every possible scenario may be happening somewhere. Civilizations that were born and disappeared, technologically advanced societies, worlds covered in eternal ice, others in flames, all coexisting within the same endless space. This multiplicity of realities makes our own place in the cosmos just one variation among infinite possibilities. The concept of infinity also challenges our understanding of natural laws. If there are infinite places, it is likely that in some of them, small variations occur, leading to different forms of matter organization, perhaps even slightly distinct physical laws. This idea brings the notion of infinity closer to the hypotheses of the multiverse, where each region may be unique. The difference is that in spatial infinity, everything would coexist within the same fabric, without the need for separate universes. Furthermore, infinity raises philosophical questions about meaning and purpose. If there are infinite copies of ourselves, then what is the value of our specific version? If everything that can happen is already happening somewhere, does our freedom of choice still matter? These reflections, although they do not change the course of science, show how the notion of infinity invades territories of the human mind that go beyond mathematics. From a practical point of view, infinity is unattainable, since we will never be able to explore even a significant fraction of the universe. But this does not diminish the power of the idea. On the contrary, it broadens our perception of cosmic greatness. To think of a universe without limits is to accept that reality is greater than any measurement or observation. It is to accept that our vision is only a fragment within something immeasurable. In the end, infinity is not just a geometric property, but an invitation to reflect on the human condition itself. It reminds us that, in the face of immensity, our understanding will always be partial, and at the same time, It inspires us to continue investigating, even knowing that we will never reach the end of the road, because the road simply has no end. When we look at the night sky, even with the most powerful telescopes, we can only see a limited fraction of the cosmos. The observable horizon works like a bubble that isolates us from the rest of reality, but science suggests that the universe does not stop there. On the contrary, there are strong reasons to believe that space continues beyond what we can see, perhaps without ever ending. This notion arises not only from intuition, but from mathematical calculations, modern physics, and the very statistical logic of the cosmos. One of the main arguments in favor of spatial continuation is the uniformity of the universe. In all directions, observations reveal practically the same distribution of galaxies, the same cosmic background radiation, and the same patterns of expansion. This isotropy indicates that the universe has no privileged center and no detectable edge. If within our observable bubble it is uniform, it is reasonable to assume that the same uniformity continues beyond it. In this scenario, the sphere of 46 billion light-years that we can observe would be only a minimal part of something much larger. Another important point comes from models of cosmic inflation. This theory describes that, in the initial instance after the Big Bang, the universe went through an extremely rapid expansion, in which space grew exponentially in a tiny fraction of a second. This growth was so gigantic that regions that were once connected became separated by unreachable distances. This means that the universe may be billions of times larger than the part we can see. Even if we may never confirm it directly, the very existence of the cosmic background radiation is a clue that inflation really occurred, supporting the hypothesis that space extends far beyond the horizon. Spatial continuation is also supported by analyses of the density of matter and energy. The universe we observe seems to be extremely balanced, with a density close to the so-called critical value. This balance suggests that the cosmos may be much larger than the observable, because a small universe would hardly have maintained such a precise adjustment. In other words, the very mathematical harmony of reality points to a space that continues beyond the limits we can see. Some theories even explore the possibility that, outside our horizon, there are regions with different characteristics. Although the laws of physics are universal, the initial conditions of the cosmos could have led to variations in the distribution of galaxies, in the formation of large structures, and even in details of local physics. This leads us to the idea that, even without being able to observe directly, what exists beyond the horizon could subtly influence what happens here. Small anomalies detected in cosmic radiation have already been interpreted by some scientists as possible signs of gigantic structures located outside the visible region. From a human perspective, this hypothesis reinforces humility in the face of immensity. We are inside an observation bubble that is nothing more than a tiny cut of reality. The universe beyond the horizon may extend indefinitely, with billions upon billions of galaxies we will never know. This idea is at the same time frustrating and inspiring. Frustrating because we will never be able to contemplate everything, but inspiring because it shows us that reality is greater than any limit we can imagine. In the end, the hypothesis of spatial continuation reminds us that the universe was not made to fit into our vision. It is larger, vaster, and more mysterious than the bubble we can observe. Even if we can never cross the cosmic horizon, science allows us to infer that the cosmos does not end there, but stretches beyond, in an endless expansion. When we talk about what lies beyond the cosmic horizon, we enter a territory where science reaches the limit of what it can affirm. Modern physics, based on general relativity and quantum mechanics, offers consistent models to describe the universe we can observe. However, when we try to go beyond this frontier, we realize that our theories are still not able to give complete answers. It is as if we were facing a locked door. We know that there is something on the other side, but we do not have the right key to open it. One of the main barriers is Albert Einstein's own general relativity. This theory describes gravity as the curvature of space-time and works perfectly on large cosmic scales. It was what allowed the calculation of the expansion of the universe and the prediction of the existence of black holes. However, when we try to apply this same theory to the initial instance of the Big Bang or to regions beyond the cosmic horizon, paradoxes emerge. Space-time seems to behave in ways that relativity cannot explain. This shows that we need a broader theory, capable of uniting relativity and quantum mechanics into a single description of reality. Quantum mechanics, in turn, is the foundation that explains the behavior of subatomic particles. It describes invisible phenomena such as superposition, entanglement, and quantum fluctuations. However, this same theory cannot, by itself, deal with the universe on a large scale. When we try to apply it to the cosmos as a whole, calculations arise that result in infinite values without physical meaning. This indicates that we still do not have a complete theoretical framework to describe what happens beyond the observable. Another limit lies in the very nature of light and information. The cosmic horizon marks the maximum point up to which we can receive signals. Nothing that is beyond can send messages that reach us, because the expanding space drags these regions out of reach. Even gravitational waves, which are distortions in the fabric of space-time, encounter similar limitations. This means that, from an experimental point of view, we are condemned never to directly see what lies beyond our visible universe. Even so, physics seeks alternative paths. Models of cosmic inflation try to predict what happens outside the observable bubble. String theory suggests that our universe may be only one layer within a larger structure. Computer simulations help visualize scenarios that we cannot measure directly, but all these advances remain in the field of hypotheses, since no direct evidence can cross the horizon barrier. This limit is not only technical, but also philosophical. What does it mean to speak of something that we will never be able to observe? To what extent is a theory about what lies beyond the horizon scientific and not merely speculative? These questions divide scientists. Some argue that we should only talk about what can be tested, while others argue that science must also explore bold hypotheses, even if they are not yet verifiable. In the end, the frontiers of current physics show us the humility of human knowledge. We have already managed to understand much about the universe, from the origin of time to the formation of galaxies, but in the face of the cosmic horizon, we must accept that we still do not have the right tools to cross it. Perhaps in the future, new theories and technologies will be able to expand our vision. For now, we can only imagine what lies beyond, using mathematics and imagination as our main lanterns in the dark. Among the boldest theories of modern physics is the idea that our universe is not all that exists, but rather only a layer within a larger structure. This notion comes from the so-called string theory, an attempt to unify all the fundamental forces of nature into a single mathematical framework. Within this theory arise the concepts of branes, which are like multidimensional surfaces on which entire universes can exist. Our cosmos would then be one of these branes, floating within a broader space called the bulk. To understand this idea, we can imagine a sheet of paper. Each sheet would represent a complete universe, with its own galaxies, stars, and planets. The bulk would be like the notebook that contains these sheets, keeping each universe separate from the others, while still being part of a larger structure. In this way, our three-dimensional universe would be only one among many possible sheets. This metaphor, although simplified, helps to visualize a reality in which multiple universes coexist, without necessarily interacting with each other. The notion that we live on a brane explains some issues that traditional physics does not resolve. For example, gravity is much weaker than the other fundamental forces, such as electromagnetism. A simple magnet can lift a paperclip against the entire gravitational pull of the Earth. Some physicists suggest that gravity seems weak because part of it may escape from our brane and spread into the bulk. This would explain why it is so difficult to detect on microscopic scales, and why it behaves differently compared to the other forces. This hypothesis also opens the way to thinking of the universe as something larger than we imagine. If our cosmos is only a brane, it is possible that other branes exist parallel to ours, each with its own laws of physics, cosmic structures, and even unimaginable forms of life. Although we have no way of directly observing these branes, mathematical theories show that their existence is not impossible. In some models, collisions between branes could even generate events similar to the Big Bang, creating new universes in an endless succession. From an experimental point of view, we still have no concrete proof of the existence of branes. However, some lines of research seek indirect signs. High-energy particle experiments, such as those conducted in colliders, search for deviations in the behavior of gravity that could indicate interactions with extra dimensions. Likewise, observations of the cosmos attempt to identify anomalous patterns that could be explained by effects coming from the bulk. So far, nothing has been confirmed, but the investigation continues. The brane hypothesis shows us that reality may be much more complex than our intuition suggests. We live in a universe that already seems immense and unfathomable, but it may be only a part of something even greater. This idea, even without confirmation, broadens our perception of the cosmos and reminds us that, in the pursuit of knowledge, what we often discover are not definitive answers, but new layers of mystery. If we accept the idea that our universe is only a brane, a membrane within a larger space called the bulk, the possibility naturally arises that there are many other branes, each carrying its own universe. This vision creates a scenario in which multiple cosmos coexist side by side, separated by invisible distances, yet still incredibly close in terms of dimensional structure. It is like imagining pages of a book. Each page is a complete universe with its own history, physical laws and cosmic structures, but no page can see the content of the other, even while being only a fraction of a millimeter apart. This layered universe model resembles a great cosmic sandwich. Each brane would be like a slice of reality, stacked with many others in an order we cannot perceive. Within each layer exist galaxies, stars, and planets, but interaction between branes would be minimal or even non-existent. The great exception would be gravity, which, according to some models, could cross from one brane to another, leaving subtle marks that we may one day detect. This detail helps explain why gravity seems so different from the other fundamental forces. Part of it could be dispersing among neighboring universes. The notion of parallel universes in layers also suggests that our reality may not be unique. Other branes could contain radically different versions of cosmos, with physical laws unlike anything we know. Imagine a universe where gravity is stronger, where atoms form differently, or where the very notion of time flows at another pace. These scenarios, though they may sound like science fiction, are logical consequences of models that seek to describe what lies beyond our horizon. There are also hypotheses of collisions between branes. In some models, the contact between two layers of universes could release an immense amount of energy, generating something similar to the Big Bang. In this case, the birth of our cosmos would have been the result of the collision between two branes, not an isolated event. This possibility opens the perspective that the creation of universes may not be a unique episode, but a continuous process in a greater reality. From an experimental point of view, proving the existence of these parallel layers is an enormous challenge. The expected effects would be far too subtle for current instruments. However, research in particle physics and cosmology continues to search for signs that our universe may be interacting with neighboring dimensions. Unexpected deviations in gravity experiments, anomalous patterns in cosmic radiation, or even particles mysteriously disappearing could be clues to this phenomenon. In the end, the hypothesis of layered branes shows us that reality may be much richer and more complex than we can perceive. We live confined to a layer of existence, but mathematics suggests that others may be beside us, as close as the back of a page, yet separated by a dimensional barrier our senses will never cross. This vision not only expands the scale of the universe, but also redefines the very concept of reality. Human experience is limited to 3 spatial dimensions: height, width, and depth, and 1 temporal dimension, the flow of time. This is the basic structure that organizes our perception of reality. However, several theories of modern physics suggest that the universe may contain additional dimensions, hidden from our sight and inaccessible directly to our senses. These extra dimensions would not be mere mathematical curiosities, but real elements of the cosmic structure, capable of influencing the behavior of particles, the strength of gravity, and even the formation of the universe as we know it. String theory is mainly responsible for popularizing the idea of extra dimensions. According to its calculations, the 4 dimensions we experience in daily life are not enough for the equations to work consistently. Up to 11 dimensions are required, so that all the fundamental forces can be unified into a single description. This means that, in addition to the space and time we perceive, there would be additional dimensions rolled up on microscopic scales, so small that we cannot detect them directly. It is as if we were living on a sheet of paper that appears flat, but at a microscopic level contains folds and invisible curves. One way to understand these extra dimensions is to imagine an ant walking on a wire. To us, the wire appears one-dimensional. The ant can only go forward or backward, but to the ant itself, there is also the possibility of moving around the circumference of the wire. This second dimension is hidden from our view, but is real for the insect walking on the surface. In the same way, extra dimensions could be around us, hidden on subatomic scales, influencing the behavior of matter without our being able to perceive them directly. One of the great implications of extra dimensions is the behavior of gravity. Unlike the other fundamental forces, gravity seems extremely weak. A simple magnet can overcome the entire gravitational pull of the Earth on a small metallic object. Some physicists suggest that this weakness is due to the fact that gravity is not confined to our 4 dimensions, but can spread through extra dimensions. If this is true, then part of the gravitational force would be dissipating into hidden realities, invisible to us. This idea is not merely speculative, but also testable in principle. High-precision experiments search for subtle deviations in the behavior of gravity on very small scales. If anomalies are detected, they could be the first evidence of dimensions beyond those we know. Likewise, particle colliders investigate whether new particles could arise as a result of interactions involving extra dimensions. So far, the results have not confirmed the hypothesis, but the search remains active and promising. The notion of hidden dimensions also impacts our understanding of the cosmos as a whole. If dimensions beyond the 4 we know exist, they may harbor different laws, unknown energy fields, and perhaps even alternative forms of organization of reality. The universe we perceive could be only a partial projection of a larger and more complex structure. This possibility redefines the very idea of space, suggesting that our vision is limited not by lack of reach, but by the absence of perception of the deeper layers of reality. In the end, extra dimensions remind us that the universe does not need to conform to what is intuitive for human beings. The cosmos may be far more intricate, hiding within its structure foundations that we are still unable to probe. These hidden dimensions may be the key to unifying physics, explaining the mystery of gravity, and revealing that reality is broader than any sensory experience we can imagine. If extra dimensions really exist, the big question is, how could they interact with our universe and leave detectable clues? Although they are invisible to our senses, these dimensions would not be mere mathematical abstractions. They could have real and measurable effects on how matter and energy behave. At this point, science seeks to understand not only whether additional dimensions exist, but also whether they communicate with our 4-dimensional world. One of the most investigated paths is gravity. Unlike the known fundamental forces, such as electromagnetism and nuclear interactions, gravity proves to be extremely weak in comparison. This raises the hypothesis that part of its intensity is being diverted into extra dimensions. Imagine gravity as the light of a flashlight. When it spreads into a wide environment, its intensity seems weaker to someone in a single point. In the same way, if gravity is distributed into hidden dimensions, its strength in our universe weakens. This model would explain why it seems so different from the other forces and opens the door to new interpretations of how the cosmos works. Experiments seek concrete signs of this interaction. In laboratories, physicists measure the strength of gravity on very small scales, trying to detect subtle deviations that could indicate the influence of additional dimensions. In particle accelerators, such as those that perform high-energy collisions, researchers look for unexpected phenomena, particles that disappear without a trace or energy that cannot be accounted for. These disappearances could be evidence that part of matter is moving into invisible dimensions. So far, results have not confirmed anything definitively, but the investigation remains active. Another field of study is related to gravitational waves. Recently discovered, these waves are ripples in the fabric of space-time caused by extreme cosmic events, such as collisions of black holes. If extra dimensions exist, it is possible that part of these waves propagate through them, modifying the signal we detect in our instruments. In the future, more sensitive observatories may analyze these patterns and perhaps reveal clues of interactions with hidden realities. The possible interactions also raise fascinating questions about what might exist on the other side of these dimensions. If particles and forces can cross invisible boundaries, Could other types of matter or energy manifest in our universe coming from them? Some theorists suggest that the mysterious phenomenon of dark matter, which makes up most of the mass of the cosmos but does not emit light, could be linked to interactions with extra dimensions. Perhaps dark matter is a form of reality spreading across layers beyond our perception, visible only through its gravity. From a philosophical point of view, thinking of dimensions interacting with our universe radically changes the idea of separation. The cosmos would no longer be an isolated stage, but part of a larger network, where different layers of reality exchange influences. This vision broadens the concept of the multiverse, transforming it into a dynamic structure in which our dimension is not alone, but only one among many. In the end, the possible interactions with extra dimensions remind us that science is only scratching the surface of reality. What we call the universe may be only a part of a much more complex cosmic organism, where forces, particles, and even gravity spread in directions we cannot yet reach. Investigating these interactions is like trying to hear an echo coming from an unknown room. We know that there is something beyond, but we are still learning to decipher the sound. Among the most intriguing ideas of modern cosmology is the hypothesis of the inflationary multiverse. It arises from the theory of cosmic inflation, which describes how, in the first instance after the Big Bang, the universe underwent an extremely rapid expansion. This expansion would not have occurred uniformly everywhere. In some regions, the process may have ended quickly, giving rise to universes like ours. In others, it could have continued, generating new regions in expansion. The result would be a scenario in which multiple universes emerge like bubbles in a cosmic ocean, in constant boiling. In this model, each universe is like a soap bubble formed on the surface of moving water. Each bubble has its own expansion, its own physical laws, and its own cosmic history. Some may be very similar to ours, while others may be radically different. The larger space that contains all these bubbles would be called the inflationary multiverse, a structure where the birth of universes is not an isolated event, but a continuous and eternal process. The idea of cosmic bubbles helps explain some characteristics of our universe. For example, cosmic inflation justifies why the observable universe is so homogeneous and flat. At the same time, it suggests that this homogeneity may be only a fragment within a greater diversity. If infinite bubbles exist, then infinite variations of universes exist, each with unique combinations of physical constants. Some could be sterile and empty, while others could harbor stars, planets, and life. This concept also raises the possibility that our universe is not the only one with favorable conditions for life. In a multiverse of infinite possibilities, there would always be regions where the fundamental constants, such as the strength of gravity, the charge of the electron, or the speed of light, assume values compatible with the formation of atoms and molecules. This cosmic diversity could explain why we live in a universe tuned to allow the existence of life, simply because among infinite attempts, some universes inevitably present the right conditions. From an observational point of view, the inflationary multiverse is extremely difficult to prove. As each bubble is isolated by the boundaries of expansion, we cannot cross from one universe to another. However, some scientists believe that subtle signs could be imprinted on the cosmic background radiation. Collisions between bubbles in the past may have left marks in the form of anomalous temperature patterns. Detecting something like this would be like finding scars of encounters between universes. So far, no conclusive evidence has been observed, but the search continues. The metaphor of soap bubbles helps us imagine the grandeur of this scenario. When a child blows several bubbles into the wind, each shines in a unique way, but all are part of the same set. So it would be with the inflationary multiverse, an ocean of universes arising, expanding, and in some cases, disappearing. This poetic image reminds us that, even in the face of the vastness of the cosmos we observe, there may be an even greater reality where our universe is just one more among countless bubbles. In the end, the hypothesis of the inflationary multiverse transforms the notion of a single cosmos into only a part of an infinite process. We live in a cosmic bubble that seems like everything to us, but that may be only a drop in a sea of realities in constant birth. This vision broadens not only the size of the universe, but also the very notion of existence, suggesting that our reality may be one among many that spring from the eternal cosmic fabric. If the inflationary multiverse really exists, with universes arising like bubbles in a cosmic ocean of eternal expansion, an inevitable question arises. What happens when these bubbles meet? The image of soap bubbles helps us understand this possibility. When two bubbles collide, their surfaces deform, merge, or even burst. On a cosmic scale, a collision between universes could generate unimaginable energy events, leaving deep marks on their structure. Some scientists suggest that such collisions could explain certain anomalies observed in the cosmic background radiation. This radiation, which is the echo of the Big Bang, should be almost perfectly uniform. But modern telescopes have already detected strange patterns, regions slightly colder or warmer than expected. One hypothesis is that these signals may be scars from ancient encounters between our universe and neighboring universes, before the boundaries of expansion separated them forever. Although no evidence is definitive, the mere possibility makes this search fascinating. The impact of a cosmic collision would depend on how the laws of physics are organized in each universe. If two universes with similar properties were to meet, the effect could be relatively smooth, producing only small distortions. But if radically different universes collided, the consequences could be catastrophic. Physical constants, fundamental forces, and even the very structure of space-time could change, perhaps resulting in the destruction of one universe or the formation of a new one. Some models even suggest that our own Big Bang may have been caused by such a collision. In this scenario, the birth of our universe would not have been an isolated and spontaneous event, but the result of a clash between two cosmic bubbles within the multiverse. This vision gives the Big Bang a new meaning, not as the absolute beginning of everything, but as part of a larger and cyclical process of continuous creation. From a scientific point of view, detecting evidence of collisions between universes is a monumental challenge. Searching for signs in the cosmic background radiation is one of the most promising strategies, but the patterns may be too subtle or confused with statistical noise. Another approach would be to look for irregularities in the distribution of galaxies or in the propagation of gravitational waves, which could carry marks of disturbances from cosmic encounters. So far, nothing has been confirmed, but the possibility keeps the scientific community attentive. From a philosophical point of view, the idea of collisions between universes expands our notion of reality. It suggests that not only do we live in a cosmic bubble surrounded by others, but that these bubbles can interact, influencing one another. This means that our universe is not an isolated stage, but part of a dynamic network where collisions and encounters shape existence. Just as stars are born from the collision of clouds of gas, entire universes could be born from the meeting of worlds beyond our imagination. In the end, the hypothesis of cosmic collisions reminds us that the universe may be more violent and dynamic than we can conceive. We live in a cosmos stable enough to allow life, but perhaps this stability is only a temporary pause in a sea of realities that collide, create, and vanish. This vision broadens the scale of creation, placing our universe as only one more episode in an eternal spectacle of cosmic birth and destruction. Among the oldest and at the same time boldest hypotheses of cosmology is the idea that the universe was not born in a single absolute event, but is part of an eternal cycle of expansion and contraction. This model, called the oscillating or cyclic universe, suggests that the Big Bang was not the beginning of everything, but only one phase of an endless process in which the cosmos expands up to a certain point, collapses upon itself, and then is reborn in a new explosion. The foundation of this theory is gravity. As the universe expands, matter and energy move farther apart, but gravity continues pulling everything inward. If there is enough mass, at some point this force would be able to slow expansion and reverse the process, initiating the so-called Big Crunch, the great cosmic collapse. In this scenario, galaxies, stars, and even space-time itself would be compressed into unimaginable density, similar to what existed before the Big Bang. The total collapse could then trigger a new explosive event, creating a new cycle of expansion. This model was especially popular before the discovery of the accelerated expansion of the universe caused by dark energy. If gravity were the dominant force on a large scale, the Big Crunch would be inevitable. However, dark energy appears to push space ever faster, reducing the chance that the cosmos will contract again. Even so, Some variations of the cyclic model remain alive, incorporating dark energy as part of the very mechanism that generates the cycles. In modern versions of the theory, the oscillating universe is not just an expansion followed by contraction. It can be seen as a sequence of rebirths, in which each cycle is not identical to the previous one, but carries traces and alterations. This creates the image of a cosmos that never had a true beginning and will never have a definitive end, but that pulses eternally through phases of creation and destruction. This vision connects surprisingly with ancient philosophies that already spoke of cosmic cycles long before modern science. The idea of cycles also helps resolve questions such as the origin of entropy. If the universe simply began with the Big Bang and moves toward a state of thermal death, entropy, the measure of disorder, would increase until it reached a maximum, and everything would end. But if the cosmos passes through cycles, each big crunch could reset part of that entropy, allowing for new beginnings. This hypothesis is still debated, but it shows how the notion of repetition can be useful to deal with fundamental problems of physics. From an observational point of view, seeking evidence for the oscillating universe is difficult, but not impossible. Some researchers investigate signals in the cosmic background radiation that could be marks of previous cycles. Others search for patterns in the distribution of galaxies that could indicate repetitions on larger scales. Although no conclusive proof exists, the idea that the Big Bang was neither the first, nor will it be the last, continues to intrigue scientists and philosophers. In the end, the hypothesis of the oscillating universe shows us a reality that is not linear, but circular. We do not live in a story with beginning, middle, and end, but in an eternal process of transformation, where each death is the prelude to a new birth. This vision challenges our intuition, but at the same time offers a comforting perspective. Perhaps the cosmos never disappears completely, but only changes form, repeating its cycle infinitely. If the universe is not a single event but part of an eternal cycle of expansions and collapses, an inevitable question arises. Could there have been universes before ours? This idea, although difficult to imagine, has been explored both by modern physicists and by ancient philosophical traditions. The cyclic model suggests that the Big Bang was not the absolute beginning, but only the most recent turn of a cycle that has repeated countless times. Thus, the universe we live in could be the heir of an endless succession of previous cosmos, each with its own history, structures, and laws of evolution. In modern cosmology, some versions of the cyclic universe theory propose that traces of previous universes could be imprinted in subtle signals within our current cosmos. The cosmic background radiation, for example, is studied in search of patterns not explained solely by our Big Bang, but which could be marks inherited from past cycles. Temperature anomalies, unusual regions of energy, or unexpected distributions of galaxies could, in principle, be echoes of a universe that existed before ours and left traces in the fabric of space-time. One of the most well-known proposals in this field comes from the physicist Roger Penrose, with the hypothesis called conformal cyclic cosmology. According to him, the universe repeats itself in eras called eons, where each cycle begins after the thermal death of the previous one. In Penrose's view, when all massive particles disappear and only photons continue to exist, space and time can be reconfigured into a new expansion. In this model, the boundary between the death of one universe and the birth of another is not a destructive explosion but a smooth transformation, where information from the past is carried into the next cycle. These ideas also find echoes in very ancient philosophical and religious traditions, which already spoke of worlds that arise and vanish repeatedly. The concept of cosmic cycles is present in texts from ancient India, in Greek philosophies, and even in mythologies that describe the creation and destruction of the universe in eternal intervals. It is interesting to see how contemporary science, when investigating mathematical models, ends up approaching ancestral intuitions about the infinite repetition of the cosmos. Even though the hypothesis of previous universes is fascinating, it faces great challenges. Detecting concrete evidence of past cycles is extremely difficult, since collapse and renewal would erase most of the information. Even so, some researchers believe that subtle signals may persist, especially in large-scale cosmic structures or distortions in the pattern of cosmic background radiation. If these clues are ever confirmed, it will radically change our understanding of the Big Bang, transforming it from an absolute origin into only another chapter in a story without beginning or end. From a philosophical point of view, thinking about universes before ours changes our perception of existence. If the cosmos has already gone through other cycles, perhaps with different physical laws, different galaxies, and even unknown forms of life, then reality becomes even vaster than we suppose. The history of the universe would not be a straight line, but an eternal circle, in which each version of reality gives way to another successively. In the end, the idea of universes before ours reinforces a vision of humility and continuity. The cosmos in which we live may not be unique, nor the first, and certainly will not be the last. Every star we see in the sky may be only a spark of the current cycle, sustained by an infinite succession of universes that once existed and universes yet to come. When we talk about the origin of the universe, we inevitably arrive at a paradox that defies human logic. Space and time, as we know them, were born together with the Big Bang. This means it makes no sense to ask what existed before or what exists outside, because the very notions of before and outside depend on space and time already existing. This limitation is one of the greatest challenges of cosmology, because our natural questions arise from everyday concepts. But the primordial universe may have followed very different rules. In Albert Einstein's general relativity, space and time form a single fabric called space-time. This fabric is not an empty stage where events take place, but a dynamic entity that bends and deforms in response to the presence of energy and matter. If space-time emerged in the Big Bang, then there was no stage before, no place, and no chronology. This idea is profoundly counterintuitive because our minds are accustomed to imagining causes, sequences, and contexts. The Big Bang breaks with this logic by presenting itself as the origin of the very stage where events occur. Even so, science tries to go beyond this barrier. Some theories suggest that the universe may have emerged from a quantum fluctuation in a primordial state, where space and time did not yet exist in the way we know them. In this case, reality could have arisen from a kind of quantum vacuum, which is not absolute emptiness but a bubbling field of energy. In this view, the Big Bang would be a phase transition, a leap in which space-time formed like a crystal emerging from a supercooled liquid. Another approach proposes that the Big Bang may have been only the passage from a previous state of the cosmos. In cyclic models, the collapse of a previous universe would give rise to a new expansion. In hypotheses related to brane theory, our universe could have been born from a collision between layers of reality in higher dimensions. These scenarios do not eliminate the paradox, but offer different ways of thinking about the origin without depending on a conventional before. The difficulty lies in reconciling general relativity, which describes the cosmos on a large scale, with quantum mechanics, which dominates the world of particles. At the instant of the Big Bang, the universe was compressed into unimaginable density and energy, requiring a theory that unifies the two pillars of physics. This theory, still non-existent, is called quantum gravity. Without it, our descriptions of the origin remain incomplete and, in many aspects, speculative. From a philosophical point of view, the paradox of beyond space and time forces us to accept the limits of language and intuition. Asking what was before the Big Bang may be as meaningless as asking what exists north of the North Pole. Our minds seek linear references, but the universe may not obey this structure. Still, the effort to formulate these questions leads us to expand our models and develop new ways of reasoning. In the end, the paradox of the origin of the cosmos is a reminder that the universe does not need to conform to our logic. The space and time that sustain us had a beginning, and everything we can observe is contained within that horizon. If there is something beyond, it escapes current understanding, remaining one of the greatest mysteries of science and philosophy. The paradox of beyond space and time is not limited to the boundaries of physics. It touches directly on the limitations of the human mind. We are used to thinking about everything in a linear way. Every event has a cause, every occurrence fits into a temporal sequence, every object occupies a place in space. But when we speak of the Big Bang and what may lie beyond it, these references simply cease to make sense. There is no before if time did not exist, There is no outside if space had not yet been born. This rupture shows that our reasoning, shaped by everyday experience, may be insufficient to understand ultimate reality. The philosophy of science recognizes this limit. Our theories are built from models and analogies that translate complex phenomena into comprehensible forms. However, these models are always approximations, not reality itself. When we reach the threshold of space-time, we enter a region where even words become fragile. How to describe something without space, without time, without causality? Many philosophers claim that, at this point, silence may be more honest than speculation. Still, science insists on exploring, because every attempt, even imperfect, opens the way for progress. The human brain evolved to deal with life on Earth, finding food, avoiding danger, orienting itself in immediate space. Our capacity for abstract reasoning is powerful, but perhaps insufficient to encompass concepts such as the origin of space-time or hidden dimensions. When we think of infinity or of realities outside time, our mind becomes confused, creating paradoxes and contradictions. This does not mean that these ideas are false, but that perhaps we need new languages and new forms of thought to fully understand them. Mathematics is one of those languages. Many times, equations manage to describe phenomena that intuition cannot reach. This was the case with Einstein's relativity, which predicted distortions in space-time before we could imagine them visually. Likewise, quantum mechanics revealed paradoxical behaviors that defy common logic, but work perfectly when described mathematically. Perhaps the same happens with the origin of the cosmos. Even if we cannot imagine what lies beyond space and time, our equations may offer clues. This cognitive limit also opens space for philosophical and spiritual interpretations. Many ancient traditions already spoke of realities beyond time, of eternity and infinity. Although science does not adopt religious explanations, it is curious to notice how the human mind has always sought ways to deal with what surpasses immediate comprehension. The paradox of beyond space and time is, in this sense, a common frontier between science and philosophy. Both recognize that there is something beyond our capacity to imagine. In the end, reflecting on the limits of human thought in the face of the cosmos invites us to humility. We do not have all the answers, and perhaps we never will, but it is precisely this lack of answers that drives us to keep asking, to create models, to develop technologies, and to expand the reach of our curiosity. The paradox of beyond space and time may never be definitively resolved, but it fulfills an essential function, to remind us that reality is greater than the mind that tries to understand it. The idea of infinity has always challenged the human mind. Long before modern science, philosophers already reflected on what it means for something to have neither beginning nor end. Infinity is not just an enormous quantity. It is the absence of limits, the impossibility of counting, the totality that escapes measurement. To think about infinity is to confront a notion that goes beyond everyday logic, and yet it is fundamental for understanding both mathematics and cosmology. In Greek philosophy, for example, Aristotle distinguished between potential infinity and actual infinity. Potential infinity is that which never ends, like a numerical sequence that can always grow. Actual infinity would be the existence of something that is already infinite in itself, without beginning or end. For Aristotle, actual infinity could not exist in the physical world, but only as a concept. This distinction still echoes today in how we deal with infinity. We accept its mathematical usefulness, but hesitate to apply it to concrete reality. With the advance of philosophy and mathematics, thinkers like Georg Cantor in the 19th century brought a new approach. Cantor showed that there are different types of infinity, some larger than others, such as the infinity of natural numbers and the infinity of real numbers. This discovery revealed that infinity is not a single and simple idea, but a complex structure with hierarchies and variations. This mathematical thought opened the way for infinity to cease being only a philosophical mystery and become a working tool in science. In cosmology, infinity has become central when discussing the shape and extent of the universe. If space is truly infinite, then all possible configurations of matter can exist somewhere. This notion approaches the philosophical idea of totality. In an infinite cosmos, nothing is excluded, but it also raises existential dilemmas. If there are infinite versions of us spread across space, What does it mean to be unique? Infinity in this sense is not only an abstraction, but a provocation to our understanding of identity and individuality. Beyond Western philosophy, many spiritual traditions have also addressed infinity as a symbol of eternity, divinity, or transcendence. Infinity, in these contexts, is not only a quantity, but a state of being. It represents that which lies beyond human understanding, something absolute and unattainable. Thus, the concept of infinity becomes a point of convergence between science, philosophy, and spirituality. Each seeks to describe it in its own way, but all recognize its power as an idea that surpasses the limits of experience. In the end, reflecting on infinity as a concept means realizing that it is, at the same time, a logical tool and a frontier of thought. It allows us to calculate, model and imagine the cosmos, but it also confronts us with the unattainable. Infinity is like a mirror that shows both the capacity of the human mind to create grand ideas and its limits when trying to fully comprehend them. While science seeks to understand the universe through observations and mathematical theories, religious and spiritual traditions offer another perspective, that the cosmos is not only matter and energy, but also an expression of transcendence. Since the earliest times, human beings have looked at the starry sky and seen not only a physical reality, but also a reflection of the divine, the eternal, and the sacred. This vision places the beyond the universe not as a spatial extension, but as a spiritual dimension that surpasses any boundary of space-time. In many religious traditions, the universe is seen as the creation of a higher entity. In Judaism, Christianity, and Islam, for example, the cosmos is born from the word and will of God, who not only creates but also sustains existence. In this context, asking what lies beyond the universe makes no sense in physical terms, because the beyond is the Creator himself, who is outside time and space. Thus, divine transcendence is the answer to what exists beyond observable reality, not another universe, but the absolute source of all existence. In Eastern traditions, such as Hinduism and Buddhism, we find the notion of cosmic cycles. The universe has neither a definitive beginning nor an ultimate end, but passes through ages of creation and destruction in eternal repetition. Here, the beyond is not only spiritual transcendence, but also the continuity of a limitless cosmic process. The universe is seen as a manifestation of the absolute, and ultimate reality is not in physical space, but in a spiritual dimension of unity, called Brahman in Hinduism, or emptiness in Buddhism. Also in ancient philosophies, such as Stoicism or Neoplatonism, the cosmos was understood as a reflection of divine order or universal reason. For the Stoics, reality was permeated by the logos, a cosmic rationality that gave meaning to everything. For the Neoplatonists, the universe was an emanation of the One, a transcendent reality beyond any description. In both cases, what lay beyond the cosmos was not a physical space, but a higher instance of existence. This religious and spiritual vision plays an important role because it answers questions that science still cannot address. When we ask what was before the Big Bang or what exists outside space and time, the scientific answer is often, we do not know. Religious traditions, on the other hand, offer answers based on faith, situating the universe within a greater context of transcendence and purpose. Even though these answers cannot be empirically verified, they continue to offer meaning to billions of people around the world. In the end, religious interpretations remind us that the universe is not only an object of study, but also a source of meaning. For some, what lies beyond the cosmos is another universe, accessible through physics. For others, it is divine eternity, inaccessible to human reason. These visions do not need to be seen as rivals, but as different ways of approaching the same mystery, the immensity of what lies beyond the visible universe. If the observable universe is only a fraction of a much larger reality, then understanding its limits and peering further requires increasingly advanced instruments. This is where the new generation of telescopes comes in, true time machines that allow us to look into the cosmic past and, at the same time, expand the horizon of human knowledge. Each new telescope launched represents not only a technological advance, but also a leap in our capacity to imagine what exists beyond. The James Webb Space Telescope, launched recently, is already opening doors to an unprecedented understanding of the cosmos. With its ability to observe in the infrared, it can capture the oldest and most distant light, emitted by galaxies formed only a few 100 million years after the Big Bang. These observations reveal not only how the universe was structured in its beginnings, but also offer clues about what may exist in regions not yet accessible to our vision. Each image from James Webb is a window into a time when space was still organizing itself, and this brings us closer to the frontier of the cosmic horizon. But the future holds even more ambitious instruments. Projects such as the extremely large telescope under construction in Chile will have mirrors dozens of meters in diameter, capable of capturing details never before seen in distant galaxies. These ground-based telescopes, combined with atmospheric correction systems, promise images with precision comparable to space telescopes, but with much greater light-collecting power. They will be able to investigate exoplanets in search of signs of life and map cosmic structures on gigantic scales. In addition, new space projects are being planned to observe the universe in different ranges of the electromagnetic spectrum. Telescopes specialized in X-rays, radio waves, and even gravitational waves promise to expand our view beyond visible light. With these instruments, we will be able to observe extreme phenomena such as merging black holes, collapsing stars, and even echoes of the very birth of the cosmos. The combination of all these data may give us an increasingly complete view of what exists beyond our horizon. These initiatives are not limited to classical astronomy. Next-generation telescopes are also essential for investigating mysterious phenomena such as dark matter and dark energy. Although invisible, these entities make up most of the universe. If we can understand how they work, we may reveal hidden aspects of the cosmos that could lead us to deeper theories about its structure. Ultimately, this could even open clues about the existence of parallel universes or extra dimensions. The impact of these telescopes is not only scientific but also philosophical. Each new image of a distant galaxy reminds us that we are looking at the childhood of the universe, at a time when space was still forming. It is like holding a mirror that reflects not only the past but also the vastness we still do not know. The future of cosmic investigations is therefore linked to the construction of these technological windows that allow us to see ever further and, at the same time, deeper into our own curiosity. In the end, next-generation telescopes are proof that humanity is not content with the limits of the visible. They represent our desire to cross the cosmic horizon, not physically, but with the light of science. And even if we never manage to see what lies beyond the observable universe, each advance brings us a little closer to the mystery that surrounds the cosmos. Exploring what exists beyond the observable universe does not depend only on more powerful telescopes. It also requires looking into the infinitely small world, where subatomic particles and fundamental forces reveal secrets that may connect directly to the origin of the cosmos. In this field, particle physics and the search for a theory of quantum gravity are the keys to understanding the limits of space and time. Large particle accelerators, such as those that collide protons at speeds close to the speed of light, function as laboratories for creating miniature universes. In these collisions, conditions reproduce on a microscopic scale, states similar to the earliest instance after the Big Bang. It is in this environment that scientists look for answers to enigmas such as the nature of dark matter, the disappearance of antimatter, and the possible existence of extra dimensions. If particles disappear or appear unexpectedly in these experiments, this may be an indication that our universe is not isolated, but connected to structures beyond what we can see. Another path is the investigation of gravitational waves. These ripples in the fabric of space-time, detected for the first time in the 21st century, open a new window into the cosmos. In the future, more sensitive observatories may record signals coming from epochs very close to the Big Bang. If we find patterns that cannot be explained only by general relativity, this may be a clue that gravity behaves differently at extreme scales, perhaps because it interacts with additional dimensions. The search for quantum gravity is perhaps the greatest challenge of current physics. While general relativity describes the universe on a large scale, and quantum mechanics governs the microscopic world, the two models do not fit in extreme situations, such as the beginning of the cosmos or inside black holes. A theory of quantum gravity could unify these two pillars, explaining the birth of space-time and revealing what exists beyond our horizon. Several proposals attempt to solve this puzzle, including string theory and loop quantum gravity. Although still hypotheses, they all point in the same direction. Reality is more complex than we can perceive. These investigations are not just theoretical exercises. They may redefine our vision of the universe and even of what it means to exist. If we discover that dark matter results from particles interacting in extra dimensions, we will be facing indirect evidence of realities beyond our own. If we manage to unify gravity with quantum mechanics, we may finally understand what occurred before the cosmic microwave background, diving into instants that today remain hidden. From a philosophical point of view, the search for quantum gravity represents the attempt to decipher the deepest code of reality. It is not only about looking at distant stars or invisible particles, but about understanding the very foundation of the cosmos. It is science trying to cross the final frontier, where space, time, energy, and matter cease to be separate concepts and merge into a single description. In the end, the future of research in particle physics and quantum gravity shows that we are still at the beginning of exploration. The universe we see is only the surface of a vaster and more enigmatic reality. Each experiment, each detection, each new theory is a step toward the unknown. Perhaps we will never directly see what lies beyond the observable universe, but we may feel its effects in particles that disappear, in waves that reverberate, or in equations that point to hidden dimensions. And it is precisely in this mystery that the strength of science resides, the ability to transform the invisible into knowledge and to expand, little by little, the limits of human imagination. Before ending this video, I want to make you a special invitation. If you made it this far, it is because you have genuine scientific curiosity and interest in the deep mysteries of the universe. That is why I ask you to leave your like, because this greatly helps spread this content to more people who are also seeking to learn. If you are not yet subscribed to the channel, take the opportunity now to subscribe and activate the notification bell. This way you will not miss any of our upcoming long documentaries about science, the cosmos, and the great enigmas of existence. And I really want to read your opinion. Comment below where you are watching this video from and what you think about what may exist beyond the universe. Your participation is essential to enrich this community and continue this journey of knowledge.